home. We do provide various online resources to keep you learning. Now, please sit back, relax, and enjoy the lecture.
Discussion on Windows Azure, and we are going to see how Facebook store their data for you. And additionally, we are going to talk about an example of a service that built on top of this systems, which is pretty famous one, which we are using every day, Google search. So before we start, it's still a good idea to give you an overview where we are coming from. So remember, we came from that, okay, this is a world of cloud computing. People want to build infrastructure on data centers, but how data centers store data? So the first example that we have shown you is the Google file system, which it has a single master server, although later on you know it's having multiple master servers, which provide a very flat structure. And the main thing why we have a flat structure, they consider the full path as a single lookup table entry. It's just because we want to save the round trip time, improve the bandwidth, the latency, and et cetera, et cetera. And another thing that is more important is that if you want to support concurrent accesses, then it becomes essential that you cannot have a design, hierarchical design that forces the all the directory inodes along the path needs to be locked, right? So that's not something encouraging concurrency. So it turns out that Google's design allows just one entry to be locked, and that's exactly the one that needs to be locked. So in this way, Google's architecture works really efficiently when you are looking up lots of data in the meantime. However, if you want to support, but the thing is that if you want to build everything in perfect ways, then that's not going to scale out economically. So turns out that this is the design decision that Google make is that, okay, we want to save money, so we want to build things on top of inexpensive hardware. So it turns out we have the replicas instead of using RAID or some other hardware techniques to ensure the correctness or say the integrity of the data. And even though the consistency or say the correctness of data is up to the applications, the designer's decision to see how are they going to handle. And the thing is that it's okay for the Google to design their infrastructure like the way how they propose is because the workload in data center at that time looks like this. They have storage based on inexpensive disks that fail frequently. So they have this master chunk server client designed with replicas. And for the large files that data centers, especially Google data centers need to deal with, they just make the chunk size larger. And for reading data, especially streams of data, large chunk also makes sense, right? And for sequential append, write only, write data, that's also large chunks that can help. right? And as we said, the flat structure is used to support multiple concurrent operation. And for bandwidth, again, large chunks wins, right? So this is examples that you can find, like the most frequently used programming model in data center, like MapReduce Spark, they all fit well in this design. However, Google's design is not perfect if you want to have a data center that needs to accommodate multiple different types of data. Like for Microsoft, because their customers not only they not only have enterprise customers, they also have end user customers like us. We play Xbox. Well, I don't play Xbox, but we have people play Xbox, right? And use like messages, play games, right? So it turns out that the data size varies. So if you have and Microsoft also have various services like Hotmail at that time, already have that service at that time, right? But Gmail is later than Google File System. So turns out that Microsoft, in the very beginning, they are aware that if you want to design something, it needs to be something that can tolerate many different types of data. And the other thing is that, well, they have customers, they have real customers, and the real customers saying that, yeah, Google assumes everyone is a good programmer, they know how to deal with the inconsistency of data. However, we are not, right? Then can you deal with that with us, right? So their data center must support strong consistency. And their customers are joint enterprises that locate everywhere. So global and scalable namespace storage, disaster recovery, because those features that needs to be there, right? Finally, because it's still a company, they want to make money. So multi-tenancy cost of storage, that's still a thing, right? So today we are going to continue the discussion on this, right? So for Windows Azure Storage, here is their overall architecture as we learned in the last lecture. And I tried to tell you that it's essentially a Google file system with many layers on top. So if you watch the string layer design carefully, you can acknowledge the string manager as the master in Google file system. An extend node is just like a chunk server in Google file system. And now the thing is that in the last lecture, we learned about what is a string, and everything here listed is true regarding a string. And we said, right, there are a few things that are interesting about the string design is that they allow like two strings to share the same set of extents, right? And as we said, cost of storage is one thing important in terms of the data center design, because the more data you need to physically store, it means that the more hard disk drive you need to consume, the more money you need to spend, right? So this design is really neat in a certain way that it's not only minimizing the time when creating a new file, because thinking about your everyday behavior, when you create a new file, it's easier to start by copying a template and then editing it, right? Then the sharing extents in the very beginning makes a lot of sense in this way, right? And the other thing is that it also helps us to save the cost of disks, because if two files, they are very similar or identical, right? You can find a lot of similarity in their extents, and we can try to share the common parts as well. So that helps to reduce the cost. So this is a really neat design. However, another thing that is also interesting is that you can see some of the extent we say is state to be sealed, and some of the extent their state is unsealed. So that's something that we don't see in Google file system. But before we talk about that, right? I try to tell you that the string layer resembles the design of Google file system. So let's look at that, right? So when you create an extent, you go to one of the string manager, and again, this string manager is like a master, right? So the string manager, one of the instance of the string manager will tell you, okay, where are the extent node that you need to update to? And once you are done with the update to the primary node, then the primary node will forward this data to other secondary. And again, similar to the Google file system design, we have 3 replicas of each piece of data. So every data will be repeated 3 times in both Google File System and Windows Azure storage. And the replication is done within the stream layer. So once the primary node receives the data and has that persistent, it returns to the customer immediately to save the time. And one thing that Google File System doesn't do, but Windows Azure that is that we have duplicated, we not only duplicate the data, but we also duplicate the Google File System, or say the stream layer, in a certain way that we clone the whole thing from one cluster to another cluster. And who coordinate is actually the partition layer, try to coordinate the inter-stem replication. And as you can see, there is no restriction saying that where the other stem needs to be located. So it could be another data located in another data center in another continent. So in this way, you can imagine that Microsoft can achieve geo-replication, which better helps for disaster recovery. So, and it's rare a case that 2 of the data centers are suffering earthquakes or volcano eruptions at the same time, right? If that happens, I believe that's probably the end of the world. And you shouldn't tweet or do any social networking at that time, right? Who cares, right? So that's actually the design of Microsoft. Now, 2 things that we found that that is different in Microsoft and Google File System is that Microsoft has the append only feature and it has the ceiling feature. So I want to ask you, why is the case? All right, let's wrap up in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so let's see, what do you guys think? Okay, most of you think it's C. So I guess to save our time, I would invite someone online to tell me what you guys think. Can someone online tell you what you think? Raise your hand. Hello, someone online. Someone online, someone online. Someone online. All right, so let me call someone. Rohit, what do you think? Okay, he is not around. James, are you around?
Can you show the slide really quick again?
Oh, shoot. Thank you. You got a good point. Yes,
Yeah.
here's the slide.
What
do you think?
Append. The first thing when I think of append only is like we're able to add stuff to the end. So so definitely strong. I can see strong consistency and and definitely one. Also number 1, just because tables and queues are really common with using stacks. And I know a global scale. I mean, append only is also scalable just because like how you went over like how we're using talk about first first out. So there's not much overhead, if that's correct. Disaster recovery, like I can't see it having any effect. Multi-tenancy and cost of storage, that's almost I don't think that has a reasoning behind it.
Okay. All right. Thanks for your insights and inputs. So here's what I think, right? So I would definitely agree with you on the strong consistency side, right? So with sealed, at least we know something sealed becomes immutable. So once something is sealed, right, you can make sure that everyone linked to that extent is guaranteed to have the states that the data is immutable and is sealed, is not going to change, right? So when you are operating on a lot of mechanisms like caching algorithm, you know, if I seal something, I cache some sealed extent that must be safe unless the file itself or say the object itself change the extent it's using. However, if you are directed to a sealed portion, then it becomes immutable and the data should be consistent there, right? So it's definitely helpful for a strong consistency, right? So once an extent is sealed, any reads from any sealed replica will always see the same content of the extent, right? So once it's sealed, it also means that every replica will see the same. So no matter which extent, the same extent, no matter which replica you are using, don't worry about if they are going to change or not, because it's now sealed, right? So it's definitely a plus for a strong consistency. Disaster recovery, I would say yes, because, but that's only by the append only part, right? So if you are append only, that makes replicas simpler because all you need to do is like, if something is already copied, I don't need to copy it again, right? All you need to do is try to copy the incremental part, right? And why disaster recovery is related to this, right? Remember how the Windows Azure supports disaster recovery. It doesn't really have anything to do if disaster happens. It just has more copies all over the world, right? However, the bandwidth among different data centers is relatively low compared against the bandwidth within the same cluster or within data center. So you really need a protocol that allows you to keep frequent replication, keep frequent synchronization among your data centers, but require least amount of traffic. So if you think about the Google file system design, you have to compare each data center. If you want to do it in a Google data center way, it turns out that you have to compare your data side by side, or at least your lookup table side by side, compare their timestamp to see if I need to copy the data, which takes a lot of time. However, if this is an append only file system, all you need to do is like, okay, when was the last time I copied stuff? And where was the location I copied to? Now, starting from that location, copy everything until the end. You're done. You're all set, right? So it's terribly easy to support data replication and handle failure scenarios in that way. Because all you need to do is to see when was the last time I copied the stuff and what's new after that. And because it's append only, so it must be sequential, logical. So then everything becomes easy to track. I would say multi-tenancy and the cost of the storage, right? Because thing that they talk about is they can apply a lot of mechanism to reduce the space used for the sealed extent. Because it's sealed, I know it's not going to change, right? So I can run duplication, I can run compression, I can do erasure coding, I can do a lot of different things to save the data copy. So it does help the cost of storage in a certain way, but these are not trivial. So don't be sad if you didn't get it right. Is that I think the answer of this question is not trivial unless you dig into the detail of the paper. So that's why I cite those sentences that would become supportive evidences why these two ideas together would support these three agendas in the Windows Azure design. All right, so I would say these three. Okay, so hopefully you can get where I'm coming from. All right, so again, right? So remember in Google file system, if write failure, it just reinitiate the write, right? But in Windows Azure, this is how they deal with that, right? So if one of the three nodes handling a write fail and the current extent is sealed and less committed boundary, the data will be on the failed node, right? So the thing is that if write fails, because you have the sealed extent still, right? So even though a write failed, the old copy of the data is still around. However, it's not the case of Google File System in a way that Google File System still allow in-place update. So it's not a pure log structure file system like Windows Azure, which means if any failure occurs in the middle, right, you can get corrupted copy of the data. And if it's unfortunate you get that data replicated to other data center disk as well, then the whole thing is messed up, right? So that's something that Windows Azure is doing a better job than Google in a way that because we have the sealed extent, and because you know the sealed extent is stored, replicated everywhere, and we just keep growing it, so we can always find a sealed extent somewhere, right? So this is how sealed extent helps addressing the strong consistency issue. And now, looking at other layers that, so now we know that stream layer is essentially a Google file system, but in fact, a better version of the Google file system by enforcing the append only feature and the sealed extent. However, on top of the Google file system, or say on top of the stream layer, they add the partition layer, which coordinates the inter-state replication. But as I said, this inter-state replication is done relatively simple in a way that all it needs to do is to check the last time we replicate data and where we copy until. Now, starting from there, everything new append there. So this is what the inter-state replication is trying to coordinate. And the other things that the partition layer would do is that it would manage the high-level data abstraction. So the interface, the front-end interface is only responsible for receiving the user request. And if the partition layer decides how am I going to store the data, and so that's the layer we decide how to manage this high-level data abstraction, like it's blob or it's table or it's message, and provide scalable object namespace. Because and that's also the feature of the partition layer by translating those object names into extents. And it's also the place where the Windows Azure handles the ordering or the consistency for objects. Because another thing that is also interesting is that in the stream layer, it only sees it only sees the mapping between the objects and the extents. However, at the layer of the partition layer, it decides how am I going to update these objects and how am I going to handle these transactions. So that's a different abstraction. So remember, the stream layer, although we have the manager, but the manager is only there for mapping. It doesn't care about the order of updates. However, for the partition layer, it will decide if I should map this update goes. And for some of you who learn transaction, you probably know the concept of transaction in a certain way. But let me give you a quick explanation on what the ordering and transaction means here is that if you think about the transaction in database, it's pretty similar this way that, okay, so saying that I have two ongoing instances that needs to update a set of objects. However, if some of them are conflict, then you should, in terms of ordering, you should then the earlier transaction pass. And when the later transaction try to commit their change, you have to fail them, and the other has to restart. So that's the concept of transaction. So that's the thing, right? So only one of the transaction gets its object updated, and the other transaction who comes later or any meaning that it has to be in a later order, its transaction must be failed and restart. So that's the transaction ordering and the consistency that Windows Azure would support, but you see nothing in Google File System, because for Google File System, it's all about a single file abstraction, and whoever comes first, whoever gets the lock, who has it, we have no idea if there is a concept of transaction, if those updates has to be in a series or not. But this is supported by Windows Azure. And again, why Windows Azure has to support it? Because they have a lot of business customers who need this kind of transaction support. And also it has to manage how which object data we need to support in stream layer. In this way, we tolerate multiple different types of objects. And it also coordinated cache and replication. So this is the concept of stream layer, partition layer. And the front end, as I mentioned, the function of front end is relatively straightforward. Just receive the user command and see how am I going to use the rest of the layers. So so now the question. So again, typically I don't talk too much about the how part, the result part for a paper, because every paper, right? So we are unfortunately living in a world that every paper is reporting positive results. So typically I don't talk too much about the result, but I do feel what this paper is presenting their result is interesting. So looking at this is how they represent their results. So the horizontal axis of this graph is the number of virtual machine instances in Windows Azure, in Windows Cloud Service, Microsoft Cloud Service. And the vertical is, well, it says entities per second is actually the, and you see the get put and fetch put. So this is the key value stores command. So what they are trying, so this is something different from Microsoft and Google, as I mentioned, right? Because they have a lot of customers relying on database to support their transaction. So they evaluate their system using real key value store applications, and they try to measure the performance of supporting key value operations. So as you can see, right, it's the vertical axis is how many key value entities per second they can serve. And the horizontal axis is the VM, number of VMs you launch for your service in the system. And one thing to find is that, well, no matter what operations you are seeing, right? When you keep increasing the virtual machine, the performance keeps scale very well, right? So their design has good scalability in a way that you look at the number of operations they can support. If you connect them together, it's a straight line. So that means good scalability, right? So a lot of people would like to misuse the word of scalability in a certain way, that they would interpret the scalability as if I add more nodes, then the performance improves. It has good scalability. That's not true. The only way we can say a system has good scalability is only when it reveals exactly the case that we have shown in this graph, in a way that when you connect all the dots together, it's a straight line. Then you can say it's a good scalability. Otherwise, it scales but not scale well. So this is a very good example of what good scalability looks like. And for this one, right, it's it's super linear scalability, to be honest. So it's better than good scalability in some sense. But one thing I do feel that they can make the paper a little bit better is that if at a point like 32, right? And if the 32 is not increasing as this, if the 32 increasing as this, it's good scalability. But if it goes this way, it's not good scalability. There's something missing in the paper, which I would complain. But generally, I think Windows Azure tried to make an argument that our solution scales really well, right? But for the Google file system, you know that there are some scalability issues there. So they draw this figure for some reason. Now, let's do a side-by-side comparison between these two. And for Google file system, they have the file, they have the chunk, they have the block. And for Windows Azure, they have the string, they have the extend, they have the record. So this is like an analogy on each side. And the storage architecture, both of them have master and chunk server. And for the Windows Azure, they call it string manager and the extend nodes. However, on Windows side, they have more string managers than a single master. So for data updates, Google File System doesn't have any restriction on that. But for Windows Azure, they only allow append only updates for a reason, because they want to support strong consistency. They want to make geo-replication easy. And the data formats for Google File System is almost only big files, but for Windows Azure, multiple types of objects. Replication, Google File System only support intra cluster replication, but not geo-replication. And for updates of nodes, for usage of nodes, both of them try to save money. So they allow the machine to be used in many ways. However, there is an interesting distinction. In Google File System, their chunk server can perform both storage and compute. However, in Windows Azure, the compute node will not be running on storage nodes. However, the way how they use machines for multi-tenancy or save the cost of machine is that they run multiple layers on top of the same node. So for example, your stream manager can be on top of an extend node. That's no problem. You can also make partition layer on top of an extend node. That's also not a problem. So they try to combine, to run multiple layers on the same machine. That's how they save the cost for multi-tenancy. However, they don't mix the storage and the compute node together because they want to provide quality of service for the customer. So that's a design decision that is slightly different between Microsoft and Google, and probably also because Microsoft was richer at that time. So that's conclude our discussion on the Google File System and the difference of Microsoft storage, and hopefully that will give you some big idea about, oh, here is what my cloud storage or cloud server looks like. And another company which is on fire these days called Facebook, right? Well, I mean, it's still, well, there is a division called Facebook, but you know the whole company is called Meta now. Let's look at how they store your data. So talk about the history first, right? And again, as I mentioned, typically in a high-tech company, they start to achieve the feature first and then try to check for performance. So in the very beginning, Facebook, they just want to provide a service, right, which is social network. And then they figure out that, okay, here's how we make money. So it's interesting. I think I kind of like told some students about this. So I think it was 2012. Okay, 2012. Yes, 2012. I was still a PhD student, which I still have a dream that I want to be a professor, which I am a professor now, right? One day, I'm at my office, Facebook called me saying that, hey, are you interested about having an interview with us? And at that time, Facebook is by no means the most famous high-tech company, because that's how they try to introduce themselves to me, is that Do you know Facebook? We are now the largest photo sharing company all over the world. Okay, so they start with being a social network company, and then they become the biggest photo sharing website, right? So that's where Facebook is, right? And so photo or this kind of multimedia, personal multimedia data become the main thing that Facebook needs to support. And in the very beginning, because just for the social network, without file sharing, the original infrastructure they use called NFS, which you are now familiar with, right, is not a big problem for that, right? Because if you are going to store those like database tables, NFS can still do a good job, right? However, right, when you have a lot of this small photo data or some small, like garbage post, like every day, those small data is going to result in an issue that we have lots of metadata, and then the NFS needs to create one for each, which is a disaster in terms of data storage, right? So, and again, right, each file access also requires this many round trips, you count it, right? So it's so complicated in a way that they have to start rethinking the design of their file system. So Facebook also have their own file system, which is part of the paper called F4 that you have read as part of it. So the title is F4, but it actually gives you a pretty good orientation about the main file system, the haystack, Facebook's photo storage, right? So that was the time when they called me saying that, well, we are the biggest photo sharing company all over the world, because at that time they already had this infrastructure to support their demand. And actually, that was one thing that I still regret why I didn't have an interview with them, right? Otherwise, I probably would be Facebook's the first couple hundred employee, and I probably owning a few houses around the Bay Area, and I'm probably retired. Right, but I didn't do that, and that's why I'm still a full professor here. All right, so here's the thing, right? So this is how Haystack works. So this is the architecture of Haystack. So the user can submit requests like, here's the photo of mine, I want to access it, right? And it goes to the Haystack cache and the content delivery network. So the Haystack cache and content delivery network is actually, you can consider them as a giant black box of caches that the content delivery network is caching the photo or the data content itself. And the Haystack cache is caching those like metadata or some information about what's in the content delivery network. Where can you get it? Right, but this is the you can consider this part as a big cache, right? And then if something I cannot find in a cache, it will go to the Haystack store. So what happens is that user send request, and the web server would go look up the Haystack directory, and again, right, the way how you look up the content in Facebook is pretty similar as Microsoft, in a way that is also using a URI format. However, what is different is that in Haystack directory, they translate the stuff into machine ID, logical volume, and folder. So these two parts is actually how they save the demand of lots of metadata for each photo. Is that the concept of Haystack is that instead of treating each single photo as a file, they treat a sequence of photos as part of a big file. So here is how they use it, right? So so they have so if you look at their format, right? They have the They have logic volume and they have the photo. And the photo, so all you need to do is in your hashtag, if you want to look up for a specific photo, is that you just tell the file system, I want to get the photo located at which volume, which location. That's it. Instead of, okay, so you probably don't build it, right? But in this way, right? The logic volume is essentially a big file that contains thousands of photos, right? And if you want to identify a photo, it's just tell the hashtag system, I want logic volume what and which photo, which number of the photo within that logic volume. That's how you address a photo, right? Remember, but remind yourself, if it's in NFS, right? Each photo must be a separate file. If you want to look up a file, you have to tell them, I want to go to this directory, I want to look up this file. And the directory has its own, I know, metadata. The file itself has its own metadata, right? So you have duplicate, you have two of the metadata at least. However, if it's haystack, it's just an entry in a lookup table again, right? Like for this user, his table or his photo or her photo is mapped to logic volume which. And the logic volume itself is considered as a giant file in the original file system. So that's just one metadata node. And instead of separating each photo as file, this giant file is just like a huge file, and you only need to tell, starting from the beginning of the file, here's the offset I can get a photo. So it's all about just one giant file as the metadata you need to store, and which offset within the file. And the offset is stored as a table entry in the haystack directory. So in this way, right, the metadata, there's only one metadata necessary for the big file. And the rest of them is still by the database table that stores the mapping between the photos. So that's the whole idea of haystack, which essentially is partition physical volume into several logical volumes, and the logical volumes are just nothing but then big files. And the big file is the metadata that you only need to store in a file system. However, the directory itself is like a big key value store table that tells you the mapping between the user object and the offset of the object in the logic volume. Then everything becomes really simple. And the offset, or say the number of photo where the photo located, is called a needle. And each needle is identified through the offset starting from the logic volume. And again, right, they also have the concept of seal. So once they find this stuff is not changing anymore, they just seal it, right? So did you find something interesting here? Seal. So what does that mean? What? The data is immutable. What does that mean? Also, as a user, did you find there is a bug here? You can't really delete it, right? So some people think about, well, once I upload some photos onto Facebook, right? If I click delete it, then it will be gone. But the thing is that with this, right? And remember, the seal is sealing the whole volume, right? The whole volume contains thousands of photos, which might not be just yours, right? Unless everyone delete those photos. Otherwise, there's no reason why they have to delete the extent, or say the volume, right? So that's something interesting about cloud storage, about that people would never think about, right? Like you think, if I delete something, it should be sanitized, right? But remember, right? Windows has seal. Facebook seals. I believe Google do it now, right? And Dropbox, I believe they do it now. Because one of the features that I really love about Dropbox is that I can undo for unlimited times. But what does that mean? Your data never gets deleted, never gets sanitized, right? So, once you read more paper, you know more. And you start to feel like, oh, privacy is never something that's achievable in the era of cloud storage because they never delete stuff for you. You saw you click the delete, your stuff is gone, your embarrassing photo is gone. No, never. Right? So one lesson I can say, probably the most important lesson, the most important takeaway for the cloud storage is that once you upload something to the internet, it will never go. It will never go away. It's always there, right? Because now everybody has the seal feature. Right? And seal is really a good feature, as we said, from the software engineering perspective. So they are never going to take it away. But well, that's a little bit deviated from what we are going to talk about. But here's the thing, right? So now we put everything in a picture, in a picture. So Google File System, we have looked at it, and the Windows we have looked at it. The Windows Azure Storage we have looked at it. And Haystack is kind of like in the middle, right? So they do not have the smallest abstraction code file or string anymore, right? They use the offset, which is just an entry in the lookup table to replace the real meaning. So they don't physically have the file abstraction. All they have is a file, or say an object is writing out the offset and the size of the object. That's all about it. There's not physically an entry or say a physical thing created for a file or a string. Instead, they only have the concept of volume and neo. That's Facebook, the big distinction between Facebook. And the master server is pretty much the directory. And the chunk server is the Haystack store. And data formats, instead of files, they have the photo and video, as I mentioned. Replication, that is a little bit interesting. So Facebook used the RAID, which is a hardware-assisted or software-assisted way that try to do inter-hard disk drive replication within the same machine. And a little bit interesting here is Google File System didn't use it for a reason, which the later paper would talk about it. But at the time that Facebook was trying to build their file system, the processor is already good enough to perform software RAID in a more efficient way. So using RAID at that time doesn't really cause too much of the increase of the cost for them. So that's why they are willing to use it. And again, they also adopt the concept of geo-replication. But but as you can see, right? So this table gives you a very good idea about what are the same, what are different among these file systems. So it seems like Haystack is a pretty good stuff. Why are we talking about F4, which is the main character of the paper? All right, let's wrap up in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so look at what you guys think. Oh, okay, this time we also get a pretty good consensus on answer C. So let me skip the discussion to save the time. So shoot. Why don't we have some of you maybe here, because I have enough of those people online. So what do you guys think about this question? What are the two that you think is correct, are correct? Number two, so it's optimized for latency of accessing data. Agree? Yes? No? Why? Why not?
I don't have a clear reason but I don't recall that.
You don't recall that in the paper. Okay. Let's put this on the shelf. How about the first one? You guys agree with that? You want to say yes?
Because it says export store volumes of one block says that you distributed at iterated coding, which uses your byte to replicate.
Yeah, but if you are, so say that again. What was that thing?
Distributed iterated coding, which uses your physical byte.
So what does that mean? So use fewer physical bytes than triple replication. So does that have anything to do? So what does that mean when you say fewer bytes? For storage, right? But is there a cost of using erasure coding? You are not sure. So interesting, right? What is erasure coding? Okay, you need to go to the actual paper. Okay, what else? Any guys here? Any guy here regarding the erasure coding? Okay, but it's some kind of coding, right? Is your data originally coded in that way? No. So what does that mean? You need to do conversion. Is the conversion free? No. What does that mean? There is a cost of what? Converting the data. Converting the data takes time. So do you think it's go faster? Okay. So now, do you still think the second thing is optimized? Not sure, right? Okay. And if you have a cost whenever you want to access the data, do you think the throughput is optimized? Not really, right? Because you are actually adding something when you are accessing the data. There is an overhead, right? So the first two cannot be true. But still, yeah, I kind of like regret that we should have this question in discussion. All right. So now, how about 3? Is it reducing the degree of data replication in the system? Yes. How come? So what are the typical number of replications we have to do? 3, right? So that's actually a magic number, right? Haystack does 3. Windows Azure, Google File System, 3, right? And how many copies this is doing? Okay, we can talk about it later, but actually 2. Right? So it's designed for reduce the degree of data replication. So one of the key goals of F4 is the storage efficiency. Reduce the effective replication factor while still maintaining a high degree of reliability and performance. How about the fourth one? I would say yes, right? Because another important goal of our storage system is fault tolerance to a hierarchy of faults to ensure we do not lose data and that storage is always available for client request. So this one is actually designed to reduce the cost, but the availability of your service. Okay, so availability, that's a different concept comparing against the first two. The first two is actually about efficiency, but availability just means that the service is available, but doesn't mean that the service has to be fast. Do you feel that? No?
So in this paper, it might be because, but just talking about availability, it means that the service should be available. It does not mean that it should be fast or slow.
Yeah, that's what I want to say, right? The availability doesn't mean it has to be fast, right? You agree?
Yes.
Yeah, right. So that's what I'm saying, right? The availability means that the service needs to be available, but doesn't have to be fast, right? So that's exactly what the paper is trying to say, right? So now, what kind of data that F4 is designed for? All right, let's wrap up in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, look at what you guys think. All right, so this time I want discussion no matter what you guys think. Let's go discussion.
I think it's 5.
5. So what's the goal? What do you think? So okay. So is F4 the only file system? And what's its mission? That's what this question is actually asking.
Oh, so they're all. So they're targeted at so all.
Yeah, you get it. All right.
Yeah, so yeah. No. Okay.
All right, let's wrap up in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, oh, more of you think it's C. Now, if you think it's C, then I would ask someone online. So I already asked James from group 1. So I would like to pick someone in group 2. So can I have, who is on group 2 today? Anyone in group 2 is volunteering to save the rest of your group? Otherwise, I'm calling. Abraham, are you around? All right, I will start with someone with from the end. Ziyuan, are you around? Ziyuan,
Yeah.
Ziyuan. Oh, okay, Sharon, okay.
Oh,
What does your group think?
oh, okay. I thought you took my name. Okay, so we had a discussion surrounding F4, the last point. F4 is optimized for.
Okay. So you guys have the agreement on the last one.
Yeah, because according to like one of my group mates, like the original his stack, it was not optimized for like it I think, if I remember he said something about it being the F4 being optimized only for one data, so he agreed with that. And for
For the rest, what do you guys think?
and F4 is optimized for. So like logically F4, the fourth point would seem correct, because like the deletes would be fewer than the reads. Sorry, the writes would be fewer than the reads. But so that way I had chosen.
So
And
you don't think 4 is correct because they are right?
the writes should be fewer than the reads, is why I feel it might be
So
optimized.
right should be fewer than reads. Okay.
And
What else?
and even and like I'm confused between 1 and 3rd. So like the third I guess.
1 and 3rd.
Yeah.
And how about frequently created deleted data?
I think like it contradicts with the read only data option, fourth one. So I don't think the second one is correct. I think I'll go with first, fourth, and fifth.
Okay. All right. So one thing interesting, huh? So now I'm asking you guys, for people online, since you have the option of raising your hand, right? So how many of you has Facebook? Raise your hand. Raise your hand. No one has Facebook? I don't believe. 5, 7, 9, okay. 10, okay. All right, so at least some of you have Facebook, right? Now, put your hands down. Now, I have the question again, right? Like, remember that when you post something, right? Like I post a photo, right? When was the time you received most likes or reactions? In the coming 30 minutes. And then what happened? Who cares? Right? Okay. And then once your data cooled down, right? Are you deleting that photo or deleting that post? No, right? The only time that I would delete something is that I broke up. Then I have to figure out that, oh, okay, this photo shouldn't show up here, right? That's the only case I will delete photo, right? Then Do you think F4 is optimized only data? Mostly. Is it frequently deleted, created? No. Right. Now, what is F4 really for? So here's the thing, right? F4 is designed for the last two. But why is that? Because Facebook observed the social network behavior is exactly as what we said, right? The horizontal axis is the time, or say the age of your data, things being shared on the social network. Vertical axis is the relative request rate, which means that the request means everything, like delete it, alter it, like it, access it, modify it, right? So in the first day, as you just mentioned, probably the first 30 minutes, depending on how many friends you have and how enthusiastic are they, right? On the first day, right? And again, okay, although this curve looks slightly, general, but this is log scale. This is log scale, log scale, log scale. So every label is actually an order of 10. So this could be, for example, this could be 10K, this could be 1K. You know what I'm saying? So this is a huge difference in scale, right? So your data is very hot on the first day. And then if you are Katy Perry, probably a week later, people still care about it. But most of the time, right, a year later, it becomes something who cares. Nobody cares, right? Like, so here's the thing, right? The temperature of the data, actually cools down as the time goes by. So Facebook did a very detailed profile of their data. They would say there are 3 different types of data. The first one is the hot data, recently created data. So people would typically post something online first, and then people like it, people react to it. And if you irritate people, that will also happen on the very first day. And then it turns out that you have to delete it, you have to modify it, right? You remember that, right? You must have done something like that, or some famous people must have done that, right? They have to retract that post, delete that tweet, right? Like Donald Trump did that a lot, right? So that's the nature of social networking. The first day, everybody cares about it, and everybody is angry about it or happy about it. And the poster, the author may make some changes to it on the first day, and people put a lot of comments on the first day. That's when it gets a lot of modification creation. Then most data will go to this category, become warm data, in a way that people not care about that much, right? But it's still there. It occasionally shows up on your recent, right? But people just score over it, right? We just look at it, and sometimes you might remember, oh, I have that photo, I check it, right? But that's it, right? Comparing with those hot data, it's not accessed that frequently. It's less frequently accessed, but there are still people care about it. There are also a certain type of unfortunate data where people don't have friends, that nobody really care about that. So it never gets, people don't care about that, right? So sometimes, right, if you have a friend that, I shouldn't say that, right? But it's really sad, right? Once in a while, you might thought about some people in your life, and you try to load his or her file. It takes such a long time. Do you have that experience? When you click someone's profile on Facebook, right? It tells you something. Right? It becomes cold data. So the thing is that, right? Okay, Facebook figure out that warm data is the data which kind of like interesting to deal with in a way that it's a vast amount of data and it's growing rapidly because Facebook's users were increasing at that time, but not for now. So the haystack, which we just studied, is designed for hot data. You see its feature, right? It reduces the amount of metadata and it's really good for accessing efficiency. However, it's too costly in a way that you have to replicate data for 3 times. It has a lot of things that will cost money. So if I want to save money, right, then I need a separate file system. So that's the philosophy of designing F4 for. So this is the storage system for Facebook right now, is that haystack, they still have it, but they reduce the scale of haystack. In the very beginning, everything is on haystack, but that's really expensive. So we don't grow the haystack anymore. In fact, haystack only used for storing hot data, for example, data that are recently created, maybe within a week. After a week, if the data is not that popular anymore, your data will be moved to warm data storage called F4. And what is F4? So it's actually a storage system designed for storage efficiency that it uses read solvent iteration coding in a way that is some kind of error correction code that use 40% of the extra overhead to store some kind of parity bits that allow us to recover data if any bits go wrong. So it's some kind of error correction code. So if you have error correction code, what does that mean? It means that you don't have to physically replicate the data itself, but you still have some sort of capability of restoring your data content if the error bits is not above a certain threshold. Right? So if your hard disk drive not really that good, but also not really that bad, the error correction code can still correct this error for you. So it's an extra overhead, but it's just 40% compared against replica that you have to do 100% application. This is a reduction. And another thing that they try to even save more money is that when they perform the geo-replication, they don't actually do full replication copy for 3 times like Microsoft and Google. Right? Instead, here's the thing, for each block, again, right, I have 1.5 times of the original size because I have the erasure coded. What they are doing is this. I took 2 blocks together and perform an exclusive OR operation. Store the exclusive OR result on another block. Can you get it? This is how they store data in terms of geo-replication. So I don't store individual block A. I don't store individual block B. I store their exclusive OR result. And if you remember what exclusive OR is about, exclusive OR tells you that if the bits are the same, the result is what? 0. If it's different, the result is 1, right? So what this block is telling you, if I have block B, it tells you if the other block at the same position is the bit representation the same or not. So what does that really tells you is that I can restore this copy if it is missing by having this 2. Right? Because exclusive OR is a reversible operation. So in this way, if this is missing, I can still compute this one using this tool. The other way around also works, right? So, but what's the cost? The computation cost, right? If one is missing, you have to perform exclusive OR operation. However, it does save the storage in a certain way, right? Right now, I don't have to do a full copy of block A or block B. Right? So you can consider this is like a 50% from each, right? And each one has 1.5 times larger. So the total space efficiency becomes 1.5 times 1.4 becomes 2.1. However, if you do replication, it's always 3. Right? And for Microsoft, is even worse because Microsoft, they provide the best solution. So they not only have the 3 replication, they also have the erasure coding. So Microsoft is actually 3 times 1.4, 4.2. Well, Microsoft is rich, right? So that's the way they can take it, right? So here's the thing, right? What's the design? Well, well, I want to say the ultimate goal of F4, again, still save money, right? But the reason is just because they want to provide economic storage for warm data. And here there are some photos description about the F4, and I think it's relatively straightforward to understand. So I'm not going through this. And again, right, if failure occurs, you have to reconstruct blocks on another drive using the remaining 2 copies of data and perform computation. So it would make the heavy disk CPU operation, but they bet this is rarely happen. So they want to save money, right, on this. And here's the performance of F4. So the latency, right, Haystack is way better. However, most of them can be satisfied within 100 milliseconds still. So overall, it's not terribly bad. And that's why the idea of F4 still stands for most of the case. So most of the time, you won't feel like my profile is way slower than Katy Perry's. Well, slightly slower, but sometimes you may blame, well, it's my browser, it's my computer, right? So it's not really distinguishable in terms of network latency. And again, there are lots of interesting things like they have their storage organization, but that's not too different between Facebook storage and others. Like they just use different naming. So they organize their data centers into a single unit called cells, which you can consider it as a stamp in Microsoft. They have 14 racks of 15 hosts, and each host contains 34 terabytes hard disk drive. And again, right, they're also using hard disk drive, but not solid state drive. So every company is trying to save money by not using the best technology, but also provide the facilities that the services that we want. Okay, so that concludes all our discussion on cloud storage. It takes longer than I would imagine. So I will leave the discussion on Google service to the next lecture, but that's a really interesting one to talk about. And before we leave the classroom, the project due today, and the very last reading quiz due next Tuesday. And don't forget to submit an iEval. We do value your opinions, and if you do that, you get a full extra credit reading quiz. And final has 2 parts, and I already published most of the logistics online. And some of you were asking about for the time limited part. I will release some practice as the midterm, what we did in the midterm. However, please don't discuss with others except for me and the TA, because I don't want people to copy or run. And you know, I was trying to be nice during the midterm that I give you very similar questions as the midterm. So don't put others into this unfair situation. Don't put me into the awkward situation that I have to deal with those skeptical tuning cases. All right. Other than that, enjoy the rest of the day, and hopefully you can tell your project, darling, you look perfect tonight. All right. See you next week.
Barefoot on the grass, we're listening to our favorite song. When you said you looked a mess, I whispered underneath my breath, but you heard it. Darling, you look perfect tonight.